last time was largely conceptual in nature. And so stuff that's conceptual in nature requires more of a discussion to kind of make sure that people are understanding where things are at. But we'll jump in today and work through more like just nuts and bolts of statistics and what am I looking at? What do these things mean? How do I go through and sort of think about distributions and stuff like that? So we'll move through pretty quickly in this with this stuff. But if something is unfamiliar or you're not quite clear, sort of slow me down and say like, hey, I have questions about that, just so we'll go through and make sure everybody's on board with things. Okay. All right. So first thing we're going to start to talk about in terms of thinking about data and distributions is our measures of central tendency. Okay. Central tendency is some index we're going to use to try and best define the center of a distribution. Okay, we're looking for the middle score. And so the idea is not just like, hey, where's the middle of this distribution? What we want to go through is say, we want to come up with a number that's most typical or representative of this group of observations. Okay, so anytime we're looking at central tendency, this is what we're trying to do. We're trying to find, certainly there are differences across individuals in this sample. What we're trying to find is the score that best describes sort of the group of scores here. Okay, and this starts to become important for between and within group comparisons. We're almost always looking at measures of central tendency with this. Okay. The issue is, and where you need to come in with your thinking cap, is that there's no one best method of determining central tendency. A lot of this is context dependent. This is a graduate level statistics. This is kind of the crux of the issue, is figuring out of my options, which one of these is going to serve me the best in doing what I'm wanting it to do here. Okay. So in this, Kate, what is, where's the center of this distribution? 100, yeah, right there in the center. Pretty easy, straightforward, right? What about this? Where's the center of this distribution?
It depends on how we're talking about center.
Okay, yeah, so let's say a little bit more about that.
So given that it's negatively skewed, your mean, median, mode aren't overlapping anymore. So if we're talking about mode, the center would be at 0. Whereas if we were talking about the mean, it would fall to the left somewhere.
Yeah.
And then median, I think, would be somewhere between the mode and mean.
Perfect answer, 100%. So you're throwing out a lot of different concepts and different approaches or measures of central tendency, right? But here we've got a negative skew. Negative skew always goes towards the tail, right? So here we've got a skew heading into the negative direction. So we've got a negative skew to this distribution, right? And as Kate is saying, whereas the center now it starts to become a little bit ambiguous, right? Here, easy peasy, everything's symmetrical. The center is pretty easy to find. Here, it kind of depends on how you want to define the center or the middle or the most representative score, right? Because these start to become now different things. What's the most representative score? Well, the most representative score is 0 because that's the most frequent. But is that the most representative? Well, we got people skewing out here to the left. How do we capture that, right? So things start to become a little bit more complex. What about this situation, Kate? Like, where's the center of this distribution?
That one's a bit more tricky to deal with.
Yeah. Why is that?
It's bimodal. So there's like 2 most like frequent answers given like the distribution. Or like, I mean, you still have the 1, but it's not normally distributed. And yeah.
Yeah, it starts to get tricky here, right? You're exactly right. What we have is a bimodal distribution. We've kind of got a thing going on here and a thing going on here, right? And if I just take the middle score, I'm going to get something maybe about here, which on the whole is most representative, but there's very, very few people who actually fall on that score, right? Here we've got a bimodal distribution. William, look at this. If this is mass, what might be going on? What might be happening here with it when we get a distribution that looks like this if we're measuring mass of, let's say, some organism?
You're sampling organisms that are either on the large end or the small end.
Yeah, yeah. And what phenomenon might we see kind of maps onto that?
Not entirely sure.
Yeah, Jack.
Maybe gender.
Yeah, sex differences, right? Now, this is body mass in grams, so these probably aren't people, right? But if these are rodents or something like that, what we might have is males and females here, right? Where we're seeing, and so this is anytime you see a bimodal distribution, what you have to start asking yourself is, do I have two distinct populations in here, right? And here, these all might be mice, right? But here we've got male mice, here we've got female mice. And if I start collapsing those together, I might be missing some important variables that sort of I should be thinking about. So again, we'll talk about this more when we're going through and doing data screening. This isn't just generating numbers to report and sort of is it above or below a threshold. Always want to be thinking about what am I seeing? What's driving the shape and characteristics of these data? And anytime I run into a bimodal thing this is very clearly bimodal, you want to make sure that the bimodality isn't a function of just the way your histogram has been some stuff, particularly if you've got just a few, like not too many observations. You can get stuff that looks like a thing that's not actually a thing, it's just kind of uniquenesses in your data. But something like this, with this number of observations, you're like, I've very clearly got two distinct populations. Do I need to be taking that into account in terms of thinking about my data? Yeah. Excellent work. Okay. So again, when we're thinking about central tendency, the approach that we take to measuring central tendency is going to be based on the shape of the distribution and the type of data. Okay. These are the things we need to be thinking about when we're choosing a measure of central tendency. Okay. So a most common measure of central tendency, the one we'll use the most in this class, is going to be our mean. Okay. In statistics terms, means are known as the first population moment. Moments are just characteristics of a distribution. Okay. So the first population moment, the first characteristic that we're thinking about is going to be the mean. Okay. Mean is easy. Mean is just the average of all observations. Okay. Here, what did someone tell me what this little thing is? I guess I'll tell you this. Yeah, what is it?
Is it like the sum of X?
Yeah, the sum of X. It's just sigma X. Right? It means people get, anybody here see sigma and sort of immediately installed with a sense of fear? Yeah, that's all right. Sigma just means adding things up. It's just mathematical shorthand. So what we're doing is we're just adding up all the X's and then we're dividing it by the sum. Pretty easy, straightforward. Calculation of the population mean, the sample mean is identical. No changes there. It's just the average. If we were talking to someone who was not a doctor of psychology, we would say it's the average, right? Other thing we can do is we can use a weighted mean. Weighted mean, we're finding the average of two samples, okay? Weighted mean, calculation of weighted mean is the sum of X's in your first sample, sum of X's in your second sample, divided by the total number of observations across both samples. This is going to give you the weighted mean. Okay. Note the weighted mean is not the average of the two sample means. Okay. Why is my weighted mean not the average of my two sample means? Yeah, William.
Oh, well, because you're taking the mean of one sample, for instance, back to the his class histogram, like you would be taking all the means of what you think are like the male mice, and then taking all the means of the female mice, so you're not actually taking the mean of the entire sample.
Yeah, exactly. Right. Let's say, sort of in your area, let's say you had a sample, sort of a normal student sample, right? And then you had maybe a sample of heavy drinkers, right? And you just took the average number of drinks from both, and then took just the average of both of those means. It would skew things around, right? When, and sort of here bonus points for this, when is the weighted mean equal to the average of the two sample means? Yeah.
I mean, I think if you have like a normally distributed data set, you took a weighted mean, which you wouldn't think would be the same.
Yep, that's true. That would, if things were perfectly normal, right? Now, that's probably not a situation we would encounter in real life, but technically, yeah, that could be a situation. Where's something when we're using actual data when my weighted mean will be equal to the average of my two means? Good.
They have the same means and same sample size?
Not the same means, but the same sample size, right? If William, in your situation, you've got 20 people from the general population and 20 heavy drinkers. If you were to take the weighted mean and then just take the average of the two means across both of those, you'd arrive at the same number, right? So if the sample sizes are identical, you can just shortcut it and average the two means, right? But in general, recognize that what's happening here, let's say I've got, William's got a sample from, like a SONA sample of 200 people, and then a sample from Aware with 50 people. If you just take the average of those two, the 50 people from Aware, that's the alcohol program on campus. It's gonna skew it way, like you're gonna get way, it's gonna look like overall people are drinking way more than they are when you've got way more observations, way more reliable observations in the sample of 200 as opposed to the sample of 50, right? And so this is where you're just taking that into account. Okay. So just some basic sort of arithmetic stuff, but important things that will sometimes trip folks up. Questions about mean? All right. So characteristics of the mean. We use the mean all the time, and mean is a pretty good metric of central tendency. Okay. What's nice about the mean is that every score in the distribution contributes. Everybody gets equal representation of mean. Any score that's in the distribution is contributing to that mean. What this means, though, is that a change in a score is going to result in the change of the mean. Depending on the size of the sample and the amount of change, it may be big, it may be small, but technically any change in a score is going to change the mean. Also, if I go through and I add a new score, it's going to change the mean. Okay. Except for when, at least when I add a new score. When can I add a new score and it's not going to change the mean?
The score is the same.
The score is the mean, right? Then it's not going to change, right? But again, we're looking at sort of very, very rare cases where that's going to happen. In general, when you're going through and working with your data, you should assume that if I pull a value out or put a value in or things along those lines, you're going to have to go through and recalculate your descriptors because it change it. And this will happen in applied research. You're like, oh, here I've gone through and got my thesis sample. Yikes, I got to go through and throw those folks out. Descriptors say we're going to need to change because that's going to change stuff, right? Or, oh, I found these other people, throw them in. It's going to change things. You know, if you got a big sample, it may not change it much, but this is science, not close enough time. So I wanted to go through and keep that. Okay. Other thing that will happen with the mean, constant added, subtracted, multiplied, or divided by every score changes the mean by that value. Okay. And we see this all the time, scaling statistical procedures and things like that. Okay. Let's say I'm measuring height in inches, right? And that's a fine way to measure height. But maybe if we're talking about the height of people, or if that's a lot of inches sometimes, what might be an easier way to describe height of people? Yeah, Catherine. Feet, yep. Want to go through and sort of describe people's height in feet, right? So what we would do is we take those measurements in inches and we divide all of them by 12. And if we go through and we do that, now we've got a different scaling, right? But what we see is that if we go through and do this, does rescaling by a constant change the shape of the distribution, Jack? No, it doesn't, right? It's identical, right? We've gone through, we've got the same data. It's just the numbers we're putting on it. It's just different units. Okay. This starts to become important when we're going through calculating z-scores and things like that, recognizing it changes the actual value, but it doesn't change the shape of the distribution. If we're sort of adding an arithmetic sort of constant to every single score in the sample. All right. So again, addition, subtraction, multiplication, division of every score by the same number doesn't change the shape of the distribution. We're going to end up. So this is a transform in terms of scaling, but it's not a transform in terms of changing your actual distribution. Feeling comfortable with this? Other thing, Kate brought up was median. Okay? Median is different. Median is the literal middle score that's splitting up your sample so that you got 50% of scores above, 50% of the scores below. Okay, so here we've got 15 scores, 1, 1, 1, 2, 2, 2, 3, 4, 6, 7, 8, 9, 9, 9. Okay, median is the one score that separates 5 on top, or 7 on top, 7 on the bottom. Median is right here in the center. Okay. Now if I have an odd number of observations, it's just the middle score. If I have an even number, what you would do is split things in half and then sort of select the middle pair. And typically what you said is the median is the midpoint of those two middle pairs, of those two middle values. So if your median, if we added a number, another 9 on the end of this, my median would be 3, and my median pair would be 3 and 4. So my median would be 3, 5, right? And the tricky thing with that is 3, 5 is not an actual observed score in here, but that's kind of the score, right? If we were to throw another 3 in here, then your middle pair would be a 3, then your median is 3, right? So just recognizing that when you go through and calculate your median may not actually be an observed score in the sample, but the same thing for the mean, right? Particularly if you're working with an ordinal scale, you're running, Charlotte, some self-report measures where you're reported whole numbers, you're gonna get a mean that doesn't actually map onto an actual ordinal score either. So it's not like it's that big of a deal in terms of median stuff. Questions about median? Last one is mode. Okay, this is just going to be the score or category with the greatest frequency. What's nice with mode is that you can use mode with any level of measurement. Okay, for mean technically you should be using continuous measures. For median you should technically be looking at ordinal scores. Mode you can use across them. Okay. And what we may see is that we have distributions sometimes that have multiple modes, right? Here we've got a bimodal distribution, got 2 most equally frequent observations. Here we've got something that's multimodal, okay? This is kind of a nice like textbook example of this that doesn't actually occur in real life. This is kind of more what it looks like, right? Is here we've got a bimodal distribution where you've got relative modes, right? You've got a major mode, which is going to be at 4, and a minor mode at 8, or excuse me, 0, right here, right? Just a way to go through part of what starts to become a steep learning curve in screening and communicating statistical information and data analysis is having the words to describe what you're seeing, right? So we've got major mode, minor mode. It's just a way of describing something that's bimodal very clearly. But we've got, so this is the major mode being its most frequent, minor mode, to second frequent. Question. Okay, so how do we go through and choose our measure of central tendency? What makes the most sense given our set of data? Generally, we're going to gravitate towards mean. Okay, means are kind of the bread and butter of inferential statistics for our means-based comparison, which I guess makes some sense. What's nice about the mean is it's typically going to be provided with representative value. Okay, and that's because every score in the distribution is included in the calculation. No one gets left out. Okay, every single value goes through and gets to contribute to the calculation of the mean. What we tend to see is greater stability across replication samples relative to the median and the mode. If we're getting something that's kind of a nice, generally sort of normal shape, my median, the middle score might jump around, sort of depending on how far I'm out, how many things I've got. So medians can jump around a little bit, mode, same thing. If you got lots of values that are all kind of around the same frequency, mode can jump around. Mean tends to be pretty stable, particularly in larger samples, which is a nice quality to have. And this is the basic for most of our inferential statistics. Even things like regression, where it's, I mean, so obviously for like ANOVA t-test, that's a literal comparison of the means, right? So those are means-based statistics, but regression is also a means-based statistic. Not that you're looking to calculate, you're looking at associations, but those associations are still calculated relative to the mean of the sample, so they continue to be described as a mean-based statistic. Limitations of the mean, though, easily influenced by extreme scores. Particularly in what situation, what's under what circumstances might means start to really impact or extreme scores really start to impact means.
Your sample's small.
Sample small, right? Like certainly if I'm measuring let's say income, right? And Bill Gates has a house in Laramie, and now all of a sudden we've got some billions of dollars that's skewing things way out of bounds. We tend to not be studying things in psychology that does that so much. And so extreme values are still a concern, but not a concern as much in sort of other areas of study. Where we start to become concerned is with small samples, okay? And for you clinical folks, this starts to become something you need to be really thinking about. Let's say, Charlotte, you're looking at like, so say aggression in kids or something like that. You only have so many observations in school, you gotta sample 20. And most kids are sort of not beating each other up. And then you got a hyper aggressive kid who's way out here. Now all of a sudden that just dropped that mean way out. So now the mean is not representative. It's, you've got a group of individuals with no aggression and one person with a lot of aggression. But if you just report the mean, it looks like you got a group with some level of aggression, right? So especially when those samples are really small, you got to watch out for what's happening and take that into account. Okay. Sometimes the value doesn't actually exist as an observed score. That's fine, but something you want to be thinking about, right? This starts to become more of an issue when someone says like the average household has, 2.4 kids, right? Like 4/10 of a kid isn't like actually a real thing, right? So I have a hard time like thinking about how to construe that as a real. It's somewhere between 3 and 4, but like so one to think about like is the mean that I'm reporting, is that actually map onto something that's a real and meaningful unit? And then our interpretation here relies on the assumption of interval data. Okay. If I'm going through it from a theory-based standpoint, if I'm calculating means, I should be thinking about continuous data that are at least interval. It doesn't have to be a ratio, but at least interval, right? How often do we measure things in psychological science that's true continuous? Not often, right? Fit if you're doing sort of physio stuff like sort of weight and things like that, then yeah, certainly. But most of the stuff we're looking at is imaginary constructs that we're documenting through self-report measures. It's not interval data, it's ordinal. So long as it's sort of got enough values, we can treat it as continuous without too much of a problem. But again, something to be thinking about in the background. What did I measure? What is the unit or level of measurement? Does this matter for the types of analyses that I want? Okay. Questions about mean and when we want to choose mean for stuff. Okay, this is going to be your go-to, but there's going to be cases where mean doesn't make sense or is just a suboptimal option. Okay. And so if mean we are having problems with mean, we might think about okay. Median has a long history in statistics, particularly early statistics, non-parametric. Who here has done sort of had stuff with like non-parametric statistics? Anybody done anything? So non-parametric stuff. Jill, did you raise your hand or were you scratching?
No, I
your
was
shit? Right. So like old school, like hand cat where you had to crank it all out by hand, right? You didn't have powerful computers to go through and do some stuff. So like old school, but they can come in handy in some cases. Non-parametric types of analyses are typically median-based analyses. Okay. So if I'm looking at data that is skewed or contains meaningful but extreme values, median can start to become useful. Okay. Let's say, Jack, So your interests, sort of personality, you do some personality. Okay, let's say you go through and you're looking at, let's say narcissistic traits or something along those lines, right? You've got a scale to measuring it. So most people are kind of hanging out here, but you get a couple of people who are pretty extreme, right? Because again, in the clinical world, oftentimes we're most interested in those extreme values. There's only going to be a handful of those ones, right? Do I want to just get rid of those and ignore those cases? No, because like those are actually the people I'm most interested in. But I don't want to calculate a mean because it's going to drag, it's going to make the whole sample look like it's more severe than it is. Here's where median based stuff can start to become useful, right? The median score on this is this, here's my range, right? Starting to add in a couple of different types of metrics to better describe what's actually going on in my sample, right? So again, if I've gone through, just because you have extreme values doesn't mean you have a problem. There's something to note, right? But then you got to think about like, what do I want? Right? Just cutting them off is an option. That's just going to leave you with a bunch of normal folks who sort of miss the point of the thing you're trying to sort of look at in the first place, right? Cindy, if we're looking at trauma exposed people and trauma reactions, we expect that pretty much everybody is going to be responding, right? And now I've got some people with some severe PTSD. Want to say, oh, they're extreme values, so we can get rid of them. No, you just got rid of the part of the sample that you were interested in. We just got to get creative use analyses to go through and account for that, right? So want to think carefully about how you're going through and managing stuff. And other thing that we'll see, as Kate reported perfectly, what we tend to see with skewed data is an ordering of our mean median. Here we've got positive skew, so tails going out to the right, sort of as the scores increase, that's where our tails getting stretched out to. What we'll see is that your mode or your most common score is going to be on the far left. Your median is, or your mean is going to get stretched out to the tail, and your median is going to be kind of right there in the middle, right? This is why for skewed distributions, particularly, median tends to be a preferred metric of central tendency, because you're not sort of going with the most common, because yes, it's the most common, but it ignores the tail. Mean is getting stretched out, so it's not representative because it's getting drug out towards the tail. Median is going to be centered in between. Same thing with the negative skew. Mean pulled out towards the tail, mode here at the end. Median is going to be sort of right here in the center. Okay. So when we're thinking about central tendency, median often used classically in skewed distributions. Now, if your skew value is an exactly 0, that doesn't mean you have to go through and jump into here. But if you got distributions that are pretty drug out, again, thinking about William alcohol use stuff tends to be pretty skewed, because you'll have some folks who are pretty far out there in terms of, depending on how you're measuring it. Oftentimes you'll end up sort of looking at this type of thing. So even with other stuff that we tend to look at, like it'll be skewed a little bit, but there are some things certainly, the same thing, sort of experimental sites for like stuff like reaction times, they're always going to be wild skewed, right? Because most people are going to be pretty quick, but then some people are goofing off, not paying attention. You get stuff dragging out towards the tail. You want to think about median-based statistics. Questions about median? All right, cool. So again, here I've got a set of scores. We've got this one score hanging way out here. Median is going to, if this is a score that is real and an accurate score, always the first thing to check, right? Is this a score of 12 or is this a score of 120? Did we have an RA added 0 onto that? Always having files to go through and be able to check and see if that's a real score. But if it is it someone who's representative of our population? Do we want to keep that in? If it's not, we cut that off, right? If I'm looking at emerging adults and measuring age, and I'm thinking about 18, 19, 20, 21, 22, 23, 24, and I got a 6-year-old student in there, that's not the person that's easy to get rid of, right? But if that is an observation that you do want to include, now we have to start thinking differently about how we go through and approach our statistics. But in terms of central tendency, median is going to be a better approach than a mean in this situation. If I have analysis that involves censored data, who knows what I mean when I talk about censored data? Sensor data is gonna be stuff where I'm going through and let's say, Jayla, you're going through and looking at like civil trials and sort of damages or things along those lines. You try to measure sort of awards and things like that. You've got sort of nothing to, you know, 10,000, 10,000 to 50,000, 50,000 to 250,000, and then above 250,000, right? You've got something that is a continuous measure, but you only measured it on your scale in an ordinal fashion. But that top category is anything from $250,000 and a penny to $6 billion, right? It's all sort of wild up there. Okay. Can I calculate a mean off of that? No, I can't, right? But what I can do oftentimes is I can go through and calculate a median. Okay. So here we've got an example where we've got interested in driving behavior, looking at miles a day that people travel, right? So 0 to 9, 10 to 19 is above the scale here. Here, I've got 100 and over. That's a censored category, right? This could be 100, it could be 500, who knows, right? I cannot just assign a number to this and then go through and calculate a mean. It's not going to be meaningful because there's a bunch of unknowns here, right? All this information is falling into the black hole and is unrecoverable. I can't sort of don't know what's happening with this, right? But what I can do is I can calculate a median, right? Because I can stack these scores up in order, find which one's the middle, and calculate a median just fine. Okay. So with sensor data, medians can be useful. So classically for skewed data, for censored data, okay, and typically by the book, ordinal scales we should be using for medians are best suited for ordinal data. Okay. Again, when we're talking about ordinal data, we're talking about some scale that has a natural order. Sort of this score is bigger than this score, right? But the actual distance between units is not going to be the same, right? So think about any self-report measure that you go through and assign that has 0, 1, 2, 3, 4, and 5, right? It's an order indicating like level of whatever it is I'm measuring. But the difference between 1 and 2 and 2 and 3 and 3 and 4 and 4 and 5 in actual real life is unknown, and it's not going to be the same. And some people's difference between 1 and 2 might be bigger than 2 and 3 on it. Like, so it's an order, but it's not a continuous measure, right? Here, median is technically the better approach to that because it's sort of capturing the true values that you actually measure. Okay. Median doesn't assume or depend on or assume equal intervals. Median is just the middle score. Okay. Now we often use ordinal data all the time, not often, always, not always, most of the time, and treat it as continuous. And we can do that generally without too much of a concern, so long as I've got a reasonable number of values there to go through and work with. But by the book, from a theory-based standpoint, medians are going to be a better approach to measuring central tendency with ordinal scores than a mean. Okay. So if I have ordinal scores 1, 2, 3, 4, and 5, I can calculate a mean of that. Median might be a better thing to think about. If I've got a sum scale that goes from 1, 2, 3, 4 in whole units to 100, probably mean is going to be fine with that, right? But just recognizing a lot of what we do this semester is realizing that what we're doing is not optimal, but sort of knowing that and understanding the implications of it. So, questions about median? Cool. Now, this is something that it's a good thing to keep in mind. Anytime I'm running analyses on transform data, what I'm doing is looking at differences in medians and not means. I'm running a means-based analysis, but sort of the metrics that I'm using as soon as I go through a transform, what I'm realistically doing is I'm looking at differences in medians across groups. Okay. Now, unlike adding, subtracting, multiplying, dividing a concept by all scores, applying a nonlinear transform is gonna change the shape of the score, but it's not gonna change the order of the scores. Okay? And when we go through, if we go through and took a look at the median of our untransformed variable and the median of our transformed variable, the people who exist at those points are gonna be the same people in both distributions. So let's say here, these are some audit data that we've collected in the lab. So this is an alcohol screener, right? And so here we've got just the raw scores, right? This is often what you see in this type of data. You got most people sort of down here, and then we've got some skew out here, sort of going through. We've got kind of a continuous distribution going up to here, and then we've got a gap, we've got a big gap out here, okay? But let's say I'm William and I'm interested in, like, these are probably the people who I'm most interested in. I don't want to just like sort of like get rid of those values and things along those lines. What I might decide I want to do is I'm going to go through and transform this, right? And audit scores are typically transformed. You see those in the literature. Is that true, or it depends on kind of the same?
Depends on the research question, but the audit scores also come with like ordinal categories people that can get sorted into.
Yeah. So kind of depending, and some things like, has anybody done reaction time work? Okay, and yeah, and Jayla, you have as well. Yeah, reaction time data is always skewed, right? So when you go through and you look at analysis, it's almost always going to be a transform of that, right? Just to kind of bring it more in line with stuff. So there's going to be some types of data where you would expect it to be transformed, and if it's not, that seems kind of strange, right? But what we see here, if we go through and take a look, if I look at the mean of this sample, it's going to be out here somewhere. The mean of this sample, it sort of changes the shape in the mean once I log transform this, okay? But if I go through and I take a look at the median of this distribution here, it's going to be at a value of 3. Look at the median of this distribution, it's 1.1. What happens if we take the natural log of 3? It's 1.1, right? So if Jayla, you're sitting here and this is you, right? In the original sample, you are sitting right at the median. You have an audit score of 3. I go through, I apply a log transform this full data set. You and all your other 3s are still right here at the median, right? Your position, the ordinal position didn't change, right? If in order of drinking, in terms of scores, it goes you, Charlotte, Jack, William. If I go through and I transform this data, the 4 of you are still in the exact same order. Your position doesn't change, the scale just changes. Now with the transform, it changes the shape of the distribution and it brings that tail in, so it's something that's more amenable to our means-based analyses. But know that when we're going through and taking a look at this, we're no longer running a means-based analysis, we're comparing medians. The median value, if I run a t-test on this, say I've got another group, I'm saying the median value of this group is higher than the median value of that group, okay? So something that starts becoming relevant and important to keep in mind. A lot of times what we do, and we'll talk about this, people go through and just transform data, then pretend that they didn't, and then treat it like it's the same score that they were using the whole time. It's not, it's a different metric, it's actually a nonlinear association that you predict. There's actually a lot of cool stuff that's going on in there. It has a lot of value to be thinking about, but we just ignore it and pretend like it didn't happen. So I need to have a high threshold before I'm going through and sort of transforming stuff because it screws with our interpretation a lot of times. But when you do need to go through and do it, just know what you're looking at. Questions about sort of transform here. We'll get into transforms more next semester than anything else. Okay. All right. Anything else on median? Feeling comfortable with this? Okay, cool. All right, mode. Mode's easy. Mode makes me happy because mode, you don't have to think about mode too much. Mode is nice because what we can use mode for is when we're looking at nominal scales. Okay. No other measure of central tendency makes sense if we're looking at nominal scales. Okay. Remember that nominal scales, we're just looking at true categories, right? This is just membership in a category, something that's sort of different. There's no order to this, right? Things like ethnicity, major, vehicle preference, right? You're you're just here. It's not so like one group is ahead of the other group and it's just, they're just different groups, right? So in that situation, what you see, watch out for this, 'cause you'll see it, is people go through, well, I've gone through and looked at vehicle preference, or sort of vehicle type. 0 is cars, 2 is trucks, 3 is motorcycles, 4 is scooters, something like that. And some goes through reports and mean. Is that useful? No, it's, you can't, there's nothing going on, right? So you want to think about, just because I assign a number to something doesn't mean I can just take a mean of it or something. So, but for nominal scales, I can say motor vehicle preference in Wyoming is to pick up truck or something like that. I think that's actually the case, but let's say it's right. So I can go through and assign a mode to that. I can also use this with discrete ordinal data counts. This starts to become useful because I'm looking at whole indivisible numbers, right? So I'm looking at the modal number of drinks students are taking and reporting in this, right? I can go through and I can say there's like number of children rooms in a residence, right? So here is the modal number, the most common thing that comes up. And then another thing we can use mode for that's useful is using this as a supplement to meet the medians and things along those lines, right? If I have like one of those bimodal distributions that we had before, right? I can report a mean and median, but none of those are actually going to capture what's going on. If I say it's a bimodal distribution, here there's a major and minor mode within this distribution. That's a much more efficient way to describe what's happening than some other measure of central tendency, right? So just adding this as a supplement. Questions? Okay. Is this sounding familiar from, so that even if you're going in the way back machine, to like sort of undergrad level stats, stuff that's been presented at some point in time? Okay, super basic, but like you would be shocked how often people screw this up in terms of like actual research, just thinking about what am I calculating, what does it mean, what's the best way to go through and describe this data. And so depending on the characteristics of the data, one to go through and make sure that you've got a measure that maps onto the actual scores that you collected. All right. Want to go through and talk about variability. Variability, incredibly important concept and something people have a hard time with. Okay. Variability, and we're going to get into different sort of terms that are close in sort of like how they sound. Variability, if I'm talking about variability in general, I'm just talking about the extent to which distribution scores are spread out, clustered together. Okay. If all the scores are the same in the sample, there is no variability. Everybody's identical. You've got a constant, right? The scores are super spread out, right? We've got a bunch of variability in this data set. Okay. We're going to go through and look at age of undergraduates on campus. Is that a distribution that's going to have a lot of variability or not a lot of variability? I would say so, like you're going to get some people out there, but most people are going to be sort of falling right here in 18, 19, 20, sort of kind of clustered in. You may have some larger stuff out there. How about this? If you go and you take a look at that age distribution at sort of University of Wyoming versus the age distribution of Laramie County Community College, LCCC, which one of those samples is going to have more variability in age? Probably community college, right? Because you're going to get people coming in from it. Here, traditional university, it's probably going to be narrow. Others, it's going to be more spread out, right? If you look at sort of the income distribution of Wyoming, it's actually not great. You got Jackson in there. Look at the income distribution, let's say South Dakota versus the income distribution of California, right? California is probably going to have much wider variability than say North Dakota or something like that, right? So thinking about how spread out or close sort of are my scores, okay? What I want you to do is think about what variability means in terms of data and the types of things that you're going through and looking at, okay? What you can think about variability, you can think about variability in terms of distance, okay? If I were to go through and randomly select any two scores from this distribution, how close or far apart are they likely to be? Okay. So if I go through and randomly pick one person, randomly pick another person, my measure of variability is going to tell me how far on average I should expect those to be. If I got a lot of variability, these two things could be wildly different. They might be identical, who knows, right? But on average, they would be pretty far apart. If I've got a set with less variability, I can randomly grab through two things and probably expect them to be reasonably close. They might not be, they might be sort of quite different, but in general, they're probably going to be about the same. Okay. As a clinical perspective, let's say I'm going through and I'm measuring depression in the general population and measuring depression in a treatment seeking sample. Which one of those samples is going to have more variability?
General population.
General population, right? My treatment folks, they're going to be systematically higher, but they're all going to be pretty close in that they're all sort of distressed people like looking for treatment, right? So I can go through and randomly pull any couple of values out of that sample, and they're probably going to be pretty close to one another. Versus if I'm in the sort of general population, I can go through and pull two, and they may be wildly different, right? So thinking about variability in terms of distance can be helpful. You can also think about variability conceptually in terms of how well any score represents your distribution as a whole. So again, thinking about if I've collected a sample, this sample is intended to represent this specific population, and the mean, I'm guessing, is equal to the population value. My measure of variability, how much error do I expect from any one individual? Okay. If I've got not a lot of variability, I'm going to say like any random selected person out of this sample is probably going to be pretty close to my percent population mean. So I'm measuring things without too much error, right? So what happens, right? This is an email chain, like who got a lot of time to just like screw around on like text messages, ha ha ha, back and forth. Knock it off. So here, if we're going to go through and sort of, I'm saying, if I got my sample is supposed to be measuring this population. I got a mean of say 20, right? And I've got a sample with not too much variability. Any randomly selected score I pull out of that is going to be pretty close to 20. I'm measuring this with sort of pretty minimal error, right? But if I go through and I'm looking at something with a lot of variability, like wide variability, here's my average, right? And this is my best population estimate. There's a lot of variability. Any individual person that I pull out of this sample could be quite a ways off of sort of the actual population value. I've got more error within this set than I would in a set with less variability. Okay, this starts to become important in terms of thinking about the precision of your measurements. Okay, again, if I go through and we talked about this before, I'm measuring height and weight by eyeballing people and picking them up and seeing how much they weigh. It's a lot of static and a lot of variability, right? Versus if I'm using good measures, much less error should be introduced to that because I'm going to be much more precise. Okay, so it makes a difference from a method standpoint, it makes a difference from a statistics standpoint, and sort of thinking conceptually about what's happening. So, questions with this? Okay, this is a critical thing. So we want you to have a good understanding of variability, kind of what this means. We get hyper focused on means, right? I would argue that variability is equally interesting in terms of sort of where things are at, right? KJ, let's say you're sort of running an experimental paradigm, so you got like a manipulation or something along those lines, right? And you're going through and it's to elicit a sort of an attitude or sort of an emotional state or something like that. And so you go through and take a look. For your outcome measure, do you want a lot of variability or a little variability based on that manipulation?
A little bit.
A little bit, yeah. Why is that?
Because then people are like responding similarly.
Exactly, right? If I've got a good manipulation, people who I put through this manipulation should land in a similar spot irrespective of who they are. If I do that, I've got a pretty good manipulation. If I've got a lot of variability in my outcome measure across this, I gotta think about like how am I doing here with this, right? Or some of my work in graduate school was working with sort of trauma related emotions and sort of analog trauma stuff. And sort of went through and presenting films to try and go through and elicit sort of emotion stuff like that. And it's fine. It's kind of what people do, but sometimes people react really well. Sometimes people don't respond at all, right? And what you want is everybody kind of like in the same space, right? And so thinking about not only looking at like, oh, how much sort of in mean units did they increase in happiness or sort of sadness or whatever, think about how variability was my or responses here, and thinking about that is something that's really, really critically important. And same thing, sort of clinical folks, right? So I've got my treatment. I got Catherine, you got your pet treatment that you're really excited about. You're seeing that, boy, people in my treatment who actually my treatment are reducing by say 15 points on whatever scale you're using, right? And I'm really hyper focused on that 15-point reduction. I'm really jazzed about it, right? Where might that 15-point reduction start to become less interesting and meaningful? Yeah, right.
It's not working.
Yeah, like on average, people go through and reduce by 15 points. But some people reduce by 20 points, and some people get 10 points worse, right? I've got a 15-point reduction, but it looks like sort of a lot of people are doing worse than when they showed up. Thinking about that variability piece starts to become really important as a critically important piece of information that we often just like delegate to an SD term and then don't think about it anymore. Should always, always, always be thinking about variability of scores, what that means in terms of like what it implies about whatever phenomenon is that we're looking at. That's my soapbox. I like variability a lot. Variability is important, but and an underappreciated piece of things, right? Questions about to think about this concept. Okay. All right. Indices of variability range. Okay. Range is just going to be the distance between the largest score and the smallest score in the distribution. Very, very basic measure of variability. A couple different ways you can calculate range. Range could be the highest minus the lowest score. And you can also calculate range as the highest minus the lowest score by it plus one. Anybody sort of, yeah, so like preferences for these ones, or having classes where sort of people tell you sort of which one of these is the better one?
Depends on if it's a population or a sample, right? Or
And that's different. That's for variance. Okay. Here, there are both ways of calculating. Like if you're in undergrad statistics course, but people get really like worked up about which one is the proper way to go through and get it doesn't matter. This is how SPSS calculates it, right? Range is a descriptive statistic. And if you've got like a lot of values, it sort of doesn't even matter at something. But just know that there are a couple different ways to go through and calculate range. And limitations of range, though, is it's determined by two extreme values. It ignores everything else in the set, right? Range can be incredibly misleading if I've got distributions with unusually large or unusually small scores, right? I have a set that's actually pretty tight, and then I've got one or two outliers out here. If I just look at the range, it's looks like I got massive variability in the set when I actually don't. It's just a couple of cases that are making that look way bigger than it is, right? And so again, because range doesn't include all score or consider all scores in the distribution, range can often be misleading in terms of variability. And generally in the positive direction, it makes it look like you have more variability in your data than you actually do. And range in and of itself, like if I'm looking at a scale, so I've got a range of 15. Range in and of itself isn't like actually like I don't find it to be a terribly useful metric. Like a min and a max is a better, is a much more informative way to go through and report this than range, right? So you'll see range reported, but just like looking at it doesn't tell me a whole lot. It tells me a little bit, but not a ton. So again, here, we've got a pretty tight set, and then so it's hanging that way out here. If I calculate the range, I've got a range of like 16 here, something like that. When in fact, everybody is pretty much just running 23 and 7, right? So range can be pretty misleading if not supplemented with other things. Other range-based statistics, okay? This will start to be important when we are thinking about interpreting homogeneous models, okay? Now, folks, you're in Tara's class, and so working with assessment stuff, so this stuff will start to become relevant and important there. Anybody else done stuff? Jack, have you done stuff with like testing and sort of looking at quartiles, percentiles, and things along those lines?
Not yet, but
Yeah. So William, have you done some stuff there? Yeah, what's context even working this stuff?
yeah, just like working with immunoassay data that can be like really large distributions. So one of the like normalization techniques we would use is quartiling the data from the immunoassays or removing the first and or just using the quartile range for analysis.
Yeah. Okay. So this is, it's kind of an old school way of going through and doing things, but something that still has uses and is helpful. Pretty good if you got like large databases, things along those lines. And what this starts to do is map on nicely to some normative data and scores. Okay. So if we're switching things into quartiles, we've got separating the 3 points that the 3 data points in a distribution where we've got 4 equal sections. Okay. Your first quartile or your Q1, this is the bottom 25% of the distribution. Okay. This is the bottom 1/4 of scores are in this in your first quartile, right? Think about this as the 25th percentile. Okay. Your second quartile, this is the center of your distribution. This is just your median, right? 50% of scores are above, 50% of the scores are below. Third quartile, this is your upper 25% of the distribution, 75th percentile. Okay. Your interquartile range is going to be the difference between your first and your third quartiles. Think about this as your middle 50, right? Your middle 50% of data is going to be contained by definition between your first and your third quartile. The other 25% above, other 25% below. It's just median based statistics wherever those cut points are, that's where they go. Okay. And as you get into some assessment related stuff, when you're looking at percentiles, things along those lines, this sort of like plays in next. So again, if we map this onto a normal curve here, right? Your median, this is your 50th percentile, this is your Q2, this is right dead center, right? Here is the point that cuts off the bottom 25% from the upper part of the distribution. Here's the point, your 75th quartile, or your third quartile, your 75th percentile, separates the top quarter from the bottom part of the distribution. And your middle 50 is right here, the sort of middle pieces here. We'll use this mostly when we're looking through it and interpreting our box plots. And we'll do a lot of box plot interpretation. This all sorts to be critical information to extract from box plots. So just make sure that you understand what this is and what this is. All right. Now, limitations here with this interquartile range tends to cut off too much of the data. If you're only looking at your interquartile range, the top 25%, the bottom 25% is gone. So you're only looking at like 50% of your scores, which is kind of the limitation with things. Now, there are cases you're using censored data analysis, which is different from the censored variable we talked about. Censoring in terms of data analysis is, it sounds like William kind of maybe some of the stuff that you're doing. Like I'm not in a situation I'm like public health type of thing. I'm not interested in like most extreme high scores, and I'm not interested in most extreme low scores. What I want to do is speak to the most sort of common sort of aspect of the population. So what I'm going to do is I'm going to cut off the top. It's usually not the top 25%, but the top, we're going to cut off the top 10% of the top 10% on the bottom. Just get rid of all those nasty sort of extreme scores. We're just going to work with a nice set that we're assuming is most representative of wherever I'm trying to work with, right? And we don't see much of that in behavioral science. But in other sort of areas, it's a pretty common thing to do, sort of like biology, wildlife, some things along those lines.
Yeah, I mean, what we were looking at was like experimental assays for new biomarkers. So like for just like dementia, Alzheimer's, CT, so it made sense to remove some of the extreme values because it were like tests that have never been done before or assays that have never been done before, so.
Yeah, so you think about like at those extreme values, probably stuff that's not reliable anyway, and just.
Because
that.
with immunoassays, there's a lot of like inherent error that can happen when running them, so.
Yeah, you're assuming if something fell that far out, there was something kind of bonkers going on with it anyway, so we just sort of get rid of that and sort of come in, yeah. Right, so again, not something you see a ton in terms of like the types of stuff that we do, but in certain fields, it is kind of the way to go through and do things. Often, and also sort of, it's easier to do in areas where you have really, really massive data sets versus like I spent all semester and got 60 observations in my experimental paradigm. Is cutting off half your sample and sort of starts to become not super attractive option of this. But if you've got thousands and tens of thousands of observations, millions of observations, losing some data isn't going to hurt you at all with that. So, okay. All right. Let's do this. Let's break early. Come back at 10 and we'll jump into variance and standard deviation stuff. I'll harass this side of the room for a bit here. So when we're thinking about variability, remembering variability as sort of a metric of distance, right? Like how far scores are close together, spread out within a distribution. Also thinking about it in terms of error, how much error are we measuring, or how representative is one random selected score. I think as we move through this semester or this year, there's going to be multiple ways conceptually to think about things. I think if you're sort of having things out there, it can kind of be the way that you think about it, and then maybe an alternative way to go through and think about it. That flexibility starts to become really useful and what will serve you much better than just like, here are the words that describe sort of what this is going on. So I just wanted to sort of encourage sort of flexible approach to thinking about variability with stuff. So we talked about range, which is a variability estimate. We also have variance and standard deviation. Okay. Variance, standard deviation, these are going to be our most common indices, right? This is the stuff that you're going to see again and again. Standard deviation, we can loosely interpret this. So this is like sort of getting pretty precise, but loosely interpret standard deviation as the average distance of any given score from the mean. Okay, and I'll talk about why this is loosely interpreted, but in general, you can think about when you see a standard deviation estimate. If you're like me, sort of when I was in your position, you see standard deviation, you're like, okay, that's like a descriptive statistic that kind of measures it, but not really thinking about what it means. Anytime you're approaching analyses, if you ask yourself, what does this literally mean? And if you can answer that, you're going to be in a much better place. Okay, standard deviation is telling you literally the average distance of any randomly selected score from the mean, right? So if I go through and I see a standard deviation of 5, what that's telling me is if I randomly select a score and look at it and see how far it is from the mean, on average, it'll be about 5 units away. Does that mean it has to be 5 units away? No, I could pull one, it could be right on the mean, be 20 units away, but on average, that's how far it's going to fall. Okay. Standard deviation is nice because standard deviation has some intrinsic conceptual meaning, and so that's why we offer for standard deviation. Variance, though, is the variance is the second population moment or the second characteristic of population distribution. Variance is going to be the square of standard deviation. It's going to be the average square distance from. This has less conceptual meaning, right? If I think about the average square distance from the mean, I'm having a hard time thinking about like what that actually looks like in practice. okay? So standard deviation, really nice because it has some conceptual meaning, but variance is gonna be sort of kind of the thing we're working with most often in terms of calculation and running our statistics. Problem is it doesn't hold a ton of interpretive value. If I tell you a scale and a metric and I give you a standard deviation, you can look at that and think about like, oh, that's maybe a lot or a little thing. If I give you the variance, you might get there eventually by turning it into a standard deviation, but it's still important from a computational standpoint. Okay. So again, direct relationship between variance and standard deviation. Variance is just going to be standard deviation squared. Standard deviation squared root of variance can move back and forth with this really, really easily. Okay. Now this is Finn, what you were alluding to.
Yeah.
Calculation of variance and standard deviation slightly different for populations and samples. Oh, I don't. There we go. All right, cool. So if we're calculating variance and standard deviation for a population, let's say we've got this set of scores here, 19587. Okay. Want you to know conceptually what we're doing here when we're calculating these values. What we're going to do is first take a deviation score for each one of these values. Deviation score, anytime you see a deviation score, it's probably going to mean the difference between an individual observation and the mean of that sample. Okay. So here, if we go through and take the mean of this set of scores, we're going to get a mean of 6. Okay. So my deviation score, if I'm going to go through and take 1 minus 6, 9 minus 6, 5 minus 6, 8 minus 6, 7 minus 6. And what I have is a column of deviation scores. This is how far each individual of those scores are off the mean. Then what I'm going to do is I'm going to calculate the square of this deviation score. Okay. So all these I'm going to square them. So -5 squared, 25, 3 squared, 9. -1 squared is 1, 2 squared is 4, 1 squared is 1. Okay. Now I've got a set of squared deviation scores. What I'm going to do is I'm going to sum those deviation scores, and that's going to give me my sum of squares. Why did I go through and square all of those scores? Jack?
So they're positive.
Yeah, why does it matter if they're positive?
Because it's a sum of squares, so like -5, that wouldn't make sense.
Yeah, yeah. What happens if Jack, if I just sum these deviation scores, what am I gonna get?
Not above 0, potentially not above 0. So
By definition, will be 0 every time, right? I can't calculate a sum of squares or a sum of anything because the sum of my deviation scores by definition will be 0, right? And so I don't get anywhere, right? But if I go through and square those, now all of a sudden I've sort of turned everything positive. I've turned everything into a square, and I can go through and square those or sum those squared deviation scores, which gives me my sum of squares. Yeah. Your sum of squares is just shorthand for the sum of the squared deviations, right? This is a very, very basic metric of variability, okay? Sum of squares, just a variability metric, okay? If variability or variance is tough to sort of wrap your head around, sum of squares is even worse. Sum of squares is a raw metric of variability, but it's not something you can look at and be like, oh, that's a lot or a little, right? If I say I've got a sum of squares of 8 billion, is that a lot or a little? Like, I don't know, it depends on the scaling, right? If we're talking about distance between planets, it's probably not that much, right? If we're talking about dollars, it's right. So again, sum of squares, as we started, this will start to become important when we get into ANOVA. Sum of squares is just a variance metric, okay? Same thing as variance, same thing as standard deviation. It's just an unscaled one that sort of doesn't carry a lot of interpretive weight on itself. Okay, so we're going to go through, we're going to calculate deviation scores, we're going to square them, add them up to get our sum of squares. And then what I'm going to do for my population variance is I'm going to divide that sum of squares by the number of observations to get my population variance. Okay, so here I'm going to go through, I'm going to take 40, I'm going to divide it by 3, 4, 5, right? And that's going to give me my variance. What I can then do is take the square root of my variance and calculate my population standard deviation. We kind of see this process. Okay. What we're doing here is we're calculating variance by definition, right? I like this a whole lot because I can look at this and I can see where this number is coming from. I personally am never comfortable with numbers if I don't understand where they came from. This helps me say, okay, I understand conceptually what these numbers mean, right? Now, do you need to do this every single time? No, that would be an efficient way to go through things. So we have a computational formula for my population sum of squares. I can take the sum of my squared x's minus the sum of my x's squared over n. Mathematically, it would be the same. It's in the same place. Okay. This is a much easier way than sort of creating down a matrix and go through and calculating this by hand. I mean, you're still calculating by hand. Just not have to do individual, sort of a bunch of individual stuff there. It reduces the computational burden. Just using your formula. All right. One of the things we want to do anytime we're calculating statistics, is we want to go through, once we have an answer, we want to go through and make sure that answer is plausible. Okay. So here we've got a set of scores. And here's the mean of this distribution. My scores range anywhere from a distance between 1 and 5. Right? As a consequence, where should my standard deviation, estimate of standard deviation fall? Be smaller than 1? No. Should it be bigger than 5? If I get an answer that's either one of those, should I think that something's gone wrong and I need to go back through and check it? Absolutely. Okay. Again, pulling from that, has anybody read that Wilkinson paper yet? It's such a great paper. I get so excited about Wilkinson. It's a weird thing to get excited about, but it's great. Like I wish before anybody like submitted a paper for publication, I wish they would have to like sort of sign the thing that said like, hey, I've read this paper before I submit this, so that you all know. It's so great paper. It's one of the quotes, there's no substitute for common sense. Never assume that a highly regarded program absolves you of responsibility for judging whether or not your results are plausible. Okay. Jen and I are working on this. We're looking, she's doing some preliminary analysis for a thesis. We're doing some factor analytic work and things along those lines and getting some solutions that like on paper, it looks just looking at numbers, they look like, oh, hey, that might be something that's sort of plausible. If you actually look and think about like what the model is saying, doesn't make any sense. I mean, it does. We understand what's methodologically going on, but from a conceptual standpoint, it's not a viable solution, right? But you only know that if you're going through looking carefully and think about like, what did I do? What does this mean? So again, like think about it, if you go through and you submit something and it's like, so like it's not like you've got an effect size of 40 or something like that. Like this is what I'm doing in my head. I'm like, if you think about that, does that make any sense? Right? Or you got this data set, you've got a mean of 7, right? Mean of 7, maybe a mean of 20, right? Like when you can't have it, there's nothing. You don't have a score that size, right? So just be thinking carefully about what did I do? Does this make sense? Before I move forward. It'll also save you a lot of time because if you catch that, hey, the number that I calculated doesn't make any sense, you can go through and correct it now as opposed to sort of spending another 15-20 minutes doing stuff before you realize that everything's gone askew, right? So always run plausibility checks with stuff. Okay. So that's good. We got our population stuff. That's good, right? Easy peasy, nothing to worry about there. Okay. But one thing to remember is that what we're trying to do with our inferential statistics is use characteristics of our sample to infer something about corresponding population parameters. Are we ever interested in our sample? Are we interested in sort of our sample characteristics? Not really, right? We're only interested in our sample so far as it's an estimate of the population. What we're interested in is populations. So could you care less about the sample, right? My null model is not about whether or not sort of my two samples are equal in something. Like that's not, I don't care about the sample values being equal. What I care about is like, do I have evidence of differences in population values, right? And so again, what we want to do is try and infer something about populations based on information over samples. And this process of inferential statistics assumes that my sample is representative of whoever I'm trying to generalize to, right? So if I'm only trying to generalize to University of Wyoming undergraduates enrolled in psychology courses, the data you get from some will be amazing. Okay. Actually, it won't be, because there's a subset of those individuals who do not do research that are sort of maybe part of, maybe of most interest to you, but still sort of want to think through some of this stuff, right? The problem is, though, when we're thinking about variability, is that if we go through and we calculate variance based on our sample, we know that samples are going to consistently underestimate our population variability. Okay. And the problem is our most extreme values. Our folks who are hanging out there on the margins are very, very, very unlikely to be captured in my sample, which then produces systematic bias in my estimates. Okay. So let's say here's my population. Okay. And we have, let's say this is, I mean, sort of normal curves, less stuff. Let's say we're looking at sort of achievement, cognitive stuff, that stuff that you're working with in Tara's class, like IQ testing and stuff like that, right? We expect this to fall on a normal distribution, right? If I go through and I collect a sample of folks, where are my observations most likely to come from? Right here in the center. That's where most of them exist, right? What I'm going to systematically miss are the folks at the very, very high end, the very, very low end. Okay. Again, if we go back to a sort of more applied example of I'm measuring height of students on campus, right? And I go through and I just kind of pick up a sample of 50 people, right? And I just hang out at Prexy's and start just grabbing people. Get a pretty good representation of folks here. This systematically, those folks on the end, they're not going to be included in my sample. And because the people on the very high end and the people on the very, very low end are not going to be captured, my sample is going to be less variable than my population is, because I'm not getting those extreme scores. Does this mess with my the estimate of my mean? No, why not, Finn?
Does that be like the mean would still account just for like the central tendency, so the extremes, not that they don't matter, but they're not as like significant.
If this is my sample, this is where my sample is coming from. I'm assuming that I'm missing some of the most extreme values. I'm missing the people who are like 7+ foot. I'm also missing the people who are under 5, right? So the idea is with means, we don't have to change the calculation of our sample mean or our population mean. Because the assumption is we're missing people from both ends. We're getting people right here, and so our mean is still unbiased, right? But if I'm looking at the variability of my sample versus the variability of the population, my sample is going to systematically underestimate the population. Most of the people are coming out of here. I'm missing that aspect of the distribution. So what happens if we just go through and we calculate our sample variance using our population formula? It's going to systematically underrepresent the true variability in the population, which is problematic. Now, quick detour into thinking about bias. Okay. You say a sample statistic is biased if the average value systematically underestimates or overestimates corresponding population. The long shot. Does anybody have a whiteboard marker? So, these are all. It's all right, we'll just use our imagination brains. Okay. Let's go through and say I go through and I measure so the mean height of students on campus, right? And so the average value is 5'8". Okay. I'm going through and as I'm going through, I got a sample of 50 folks. Is my sample mean going to be 5'8" exactly? Maybe it's 5'9", 5'8". So I run another sample. It's a little shorter. And I run another sample, maybe it's way over because I got a bunch of basketball players on accident, and I do run it again, it's way short. So like, but on average, if we go through and think about the sampling distribution of means, if I look at all possible means of sample size 50 that could be drawn from the population, the mean of that distribution of sample means is going to be equal to population value. So I've got an unbiased statistic. On average, the value of any individual's, on average, the value of my samples that I could collect are equal to the population parameter. I've got an unbiased statistic. Okay. If though, the average of my sample, potential samples systematically overestimates or underestimates that population parameter, now I've got a biased statistic. And if I'm calculating sample variance using the population formula, how is that statistic going to be biased? An underestimate or overestimate? It's going to underestimate, right? It's going to be systematically smaller than the true population value. True population variance is this, right? But even across repeated estimates, if all of my sample estimates are consistently underestimating the population variance, the mean of all my variance estimates is going to be too small. And so I've got a biased statistic here. Good thing though is we can correct this bias with a really, really, really minor adjustment of our formula. What we're going to do when we're calculating sample variance is we're going to take our sum of squares that we calculated for a sample and we're going to divide it by n-1. And what happens if our concern is that our sample, our estimate of our population variance based on our sample is going to be too small based on sort of the standard formula? What I do is instead of taking my sum of squares and divide it by the number of observations in the sample, I take it and divide it by the number of the observation by sample, so -1. What this is going to do is it's going to make my denominator smaller. And as my denominator gets smaller, what happens to my outcome? It gets bigger. Okay. Here's another thing. Almost everything we do this semester is going to break down into ratios, right? So thinking carefully about what happens if my denominator is bigger and smaller, what happens if my numerator is bigger and smaller, the outcome statistic is a really, really, really effective way to go through and start thinking conceptually what's happening within our statistical models. Okay. So here, what we have is a flexible adjustment. Taking our population formula and we're just taking the denominator is just not n, the number of observations, this number of observations -1. Okay. So if I go through and I have a very, 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 very large sample, Charlotte, what's the adjustment going to be right here?
Sorry.
If I have a really, really large sample and I'm just going to take my sum of squares and divide it by n-1 instead of n, what's the adjustment going to be on my variance estimate here?
It'll be larger than it would have been.
What's that?
It'll be larger than it would
It'll
have
be
been.
larger than it would have been, but is it going to be a big adjustment or a small adjustment?
Oh, not a small
It's going
adjustment.
to be really, if my sample is really, really big, it's going to be minuscule, right? What if I have a sample of 20? It's going to be big, right? Which starts to make sense in terms of thinking about this as an unbiased statistic. As my samples get bigger and bigger and bigger and bigger and bigger, what's more likely to happen? If I go through and I'm measuring height of students and I have a sample of 20 versus a sample of 500, I'm more likely to catch these out. So the adjustment that I need to make onto that is going to need to be smaller to the point where it gets functionally, if my sample is large enough, I'm functionally just actually calculating a population estimate. But if we're in psychology and we're historically working with very, very small samples, 15, 20, 25, 30, something along those lines, this makes an important adjustment because the people that I've got my sample of 30 almost certainly aren't calculating those folks or capturing those folks. And if they did, someone maybe thoughtlessly threw them out because they're an outlier and so they're problematic. So thinking about this as a really slick, I'm not sure why n-1 works. It does mathematically, but it's slick and elegant. That's all you have to do to make that adjustment. But this then turns this into an unbiased assessment of population variance. Questions? Yes.
kind of just answered it, but I was gonna ask why and -1, like why not and by
That I,
2?
that I don't know. That would require probably proofs on the board, and so this isn't an econometrics class, and so like, there's some things that I'm comfortable with saying, like, guessing this has probably been worked out since the twenties, the 1920s, right? Yeah, we'll accept this, but it's a pretty slick, so long as, because we always you go through this in undergrad back, here's the population formula, here's the sample form, but no one really explains why. This is why, and if we're thinking carefully about statistics and what's happening, I think it's a good thought exercise to understand why we're doing things the way we are. Because this starts to become an issue too, when we're going through and looking at when you get into SEM programs like M plus and things along those lines, right? What you do is you'll be getting coefficients, tested coefficients that are calculated as z-scores, right? The z-score is a population estimate. We don't have, we're using samples, right? Probably, well, the issue is they can go through and do that because if you're running an SEM, you should have enough people in there so that functionally the correction you would make for this is trivial and not important. So they're just reporting that, right? So understanding what's happening, why things are happening, and sort of importantly being able to respond to people who, like, will get real up in arms about something and they have to do it this way. Like, well, actually, you know, because that's for this situation, right? So I just wanted you to understand kind of where some of this stuff is coming from. So questions about why we're going through and sort of making this adjustment? Feel okay about this? Okay, cool. So going back to our previous set, we're going to take this before we were treating this as a population of 5. Here we're saying we've got a sample of 5. Okay, so again, we've got the same scores. We're going to first calculate deviation scores, same as we did before. Going to square our deviation scores, and then we're going to calculate our sum scores. Okay, nothing has changed. The exact same thing. All we're going to do now is we're going to now divide, once we got our sum squares, we're going to divide our sum of squares by the number of scores -1 to give us the sample variance. And then we can take the square root of that to get our sample standard deviation. But again, the computational formula for your sum of squares is exactly the same. We didn't change anything there, right? We're just making that correction to adjust for the sample. And if our sample is really large, difference between 500 and 499 is not going to make any amount of difference. The difference between 15 and 14 will make it pretty sure. So think about population versus sample variability, right? So in these scores that we just calculated, right? Sum of squares stays the same, but we see changes in the variance here, right? If our population only has those 5 observations, we've got a variance of 8, a standard deviation of 2.3, okay? But if we're saying that this selection of 5 scores is representative of a larger population, and we would for sure expect a sample of 5 to wildly underestimate our population variance, you can see that variance increases and standard deviation increases here to make that adjustment for the sample versus the population. So again, sum scores formula is the same. Variance estimate, you're just going n minus 1 instead of n, and then to get this, you just take the square root of your variance. Okay. Here's the thing: when you're running calculations, work with variance. Okay, variance is kind of your base unit. It will sort of save you time. Sort of at the end of it, so you want to calculate a standard deviation, do that. But for computational purposes, you should be working with variance. Think about variance as your computational metric, and standard deviation being more descriptive. That's kind of what you're just creating. Questions about this? Okay. So going back to and just re-hitting the utility of our standard deviation, again, thinking about this as conceptualizing variability in our set as measuring typical distance from the mean on average, how much should I expect things to jump around? I mean, so mean distribution, some scores will go close to the mean, others can be farther away. But if I know both mean and standard deviation, what I can start to do it gives me information about the distribution of scores, right? I can go through and look at this paper and say, here's the mean standard deviation. Here's a different paper, here's the mean standard deviation. Does it look like these scores were generally comparable, or are we seeing wild differences across these two? Okay, and focusing on both, not just the mean, starts to become important. Okay, if I see a mean difference of this paper has a mean of 20 and this paper has a mean of 30, is that a big discrepancy or a small discrepancy? I don't know, depends on variability, right? If this one has a mean of 30, 20, and this one has a mean of 30, and standard deviation is 2, is that a big difference or not a big difference? Pretty big difference, right? If this has 20 and this has 30 and it's got a standard deviation of 25, is that a big difference, meaningful difference? Not really, because scores jump all over the place, right? So wanting to think carefully and sort of incorporate this to start to make inferences about sample characteristics. What we can also do is start to think about using means and standard deviations in terms of making assumptions about how representative or likely a score is in a distribution. Okay. Now, if I have something that has a reasonably normal distribution, that standard deviation starts to tell me sort of about kind of where this is likely to fall on the distribution. Okay. Now, if we have a true normal curve, right? What we know is that if I have some variable or something that I'm measuring on a normal curve, about 2/3 of my scores are going to fall within a standard deviation above below me. When we go out to 2 standard deviations, I've got about 95% of the distribution is going to fall there. 3 standard deviations, over 99% of the distribution is going to fall between a standard deviation above and below. So if I've got a normal distribution, right, and Jack, I say, oh, hey, this score falls 3.5 standard deviations from the mean. Is that a common score or a rare score?
Rare score.
Super rare, right? So if we've got a true normal distribution, now this is again all predicated on something being sort of reasonably normally distributed. But if it is, I've got someone 3.5 standard deviations above, they're out here, right? That's in the very sort of bottom of the tail. That's a really, really rare score, right? That's kind of a unique thing, right? If I've got someone who is, 3/4 of a standard deviation, that's normal. They're just kind of right there where we expect most people to be, right? Even here, 95% within a couple standard deviations, right? So it's starting with mean and standard deviation. If I can assume that whatever we're looking at is sort of existing on a reasonably normal distribution, I can start to sort of make inferences about how likely or how common sort of this score is or how rare it is to kill those ones. Questions? All right, cool. So again, like thinking about this, right? So I've got, if we're saying the height of adult men is in the population is 5'10" with a standard deviation of 3, right? Start to make inferences about sort of how extreme are these scores, right? This first person, William, is this an extreme score?
I would say no,
Why not?
because he's within 2 standard deviations of the mean.
Yeah, right. So we're within 1 1/3 standard deviation. So someone who is on the smaller end, but not too bad. What about this gentleman here? Yeah, right. We got someone who's getting close to 3 standard deviations above the mean. That's sort of getting pretty thin, right? If that's over 99% of the distribution within 3 standard deviations. So this individual, yeah, this is going to be on the smaller end, right? We're over 2 standard deviations below, right? So with this, I can start to sort of go through and make assumptions about how representative or how rare or likely this score is, right? So this becomes easy, right? Because we just, honestly, I probably don't need means and standard deviations. If I say like these are adult men, and I can go through and take a look at that, I reasonably know are these sort of normative scores, high or low scores. But what if we start going through and getting into a behavioral science land where metrics are not important or carry no intrinsic value? Now all of a sudden I'm completely lost, right? You say Bert has an extroversion score of 120. I don't know. It's like, I don't know, that could mean anything, right? For you clinical folks, when you're going through, you're writing up assessment reports, right? Just going through and writing the report or writing the mean of some score or an score on some measure is useless and meaningless unless someone is very, very familiar with that measure. It's not helpful, right? Because no one really does those metrics, so the metrics not real, right? But if you can start to put in normative scores, right? So for help seeking samples, sort of average score is this with a standard deviation to this. That now all of a sudden helps me say like, oh, this person is about where we would expect help seeking people to be. Or here in sort of normative college population, this is sort of mean and standard deviation. This person is actually quite a bit above, right? Now all of a sudden I can start to make sense of this, right? So here we've got 3 different scores. These by themselves are meaningless. I don't know what this means, right? But I start dropping in so some reference mean standard deviations for some estimate of the population. Now all of a sudden this is starting to be okay. This person is moving up there in terms of stuff, right? This person is close to 2 standard deviations above the mean, right? So we've got higher levels of extroversion, even more, right? Here, this is looking pretty low, right? So we get into just an incredible amount of information in terms of interpreting and understanding phenomena with the inclusion of some of these descriptive statistics, okay? So always, word your descriptives somewhere, either in text, in a table. Trust me, you have not maybe hit this point yet, but eventually you're going to be looking at trying to put together a thesis or sort of a dissertation or something like that. You're really going to want to know what those descriptive statistics are for calculating something that person will not have reported them. Right. So don't contribute to that in your own work. Always make sure you got your descriptives in somewhere. So again, if we're going through and thinking about how our standard deviation starts to play into our inferential statistics, and we'll get into this in more depth. In general, you can think about our inferential statistics. This is anything with a p-value, right? Is we're trying to differentiate signal from noise. Okay. Is what I'm seeing in these data actually representative or reflective of a population, or am I just seeing random fluctuations? What do we call random fluctuations? Okay.
You repeat that, like.
Yeah, what do we call random fluctuations? See the data said. Charlotte, can you help her?
Is that simpler?
It's sampling error, right? It's just the deviation, the difference between your sample statistic and your population parameter, right? And this is what we're looking at. Like, are the differences that we're seeing across these means, across these stuff, is this reflective of true population level differences? Or is this just, yeah, I'm going to collect samples that are going to kind of bounce around a little bit, right? That's what we're looking at. We're trying to say, is this sampling error or is this sort of true differences? Okay. And so when I was going through and I was saying, so we gave the estimate of, here's the difference between 20 and 30. Is that a lot or a little? So based on sort of standard deviation estimates, I saw a couple of people like, what's that talking about? Like, what we're seeing here is we're talking about the difference in being able to see patterns with in data with high levels of variability versus low levels of variability. Okay, if I have pattern data with low levels of variability, everything's pretty tight, right? My variability in the data is not big. It's pretty easy to see patterns. Things start to separate pretty easily. Okay, if I've got differences with higher levels of variability, it's a harder thing to go through it and see. Right, so I said the difference between mean of 20, mean of 30, right? If I've got standard deviations in both of these populations of 5, variability is pretty tight, the difference is big, it's going to be pretty easy to see that these are representative and different, right? Now we got one sample 30, one sample 20, one sample of 30, standard deviation is 25. There's a lot of overlap in those distributions. It's really hard to pick up if what I'm seeing is just some differences in terms of sample, or if that's true population differences. Okay. So if I go through and I got two experiments here, okay? Experiment one, we've got 1 and 2. Experiment B, we have group A, group B. Jayla, which one of these are we seeing? Which one of these is it easier to detect group level differences in experiment A or experimental B? Yeah, why's that?
There's less variability between the scores.
Yeah, within each group, everybody's kind of this is your type manipulation, right? Where everybody in group 1, everybody in group 2, they're all scoring about the same, right? Like I've got a really effective manipulation, everything's pretty clean, right? Here, we're kind of all over the place, right? Here, it's pretty easy to see group 2 is scoring above group 1. I don't know, it looks like maybe group B is scoring above group A, which it is. There's just so much variability in there, it makes it hard to see, right? And if we go through and plot this out, we can see this, right? Here is our experiment A, right? Here's our first group, here's our second group. Jayla, you've gone through and you've developed an amazing manipulation. It separates people out. Everybody's really consistent and tight. And it's really, really easy. There's hardly any overlap in these distributions. It's very clear that we've got two different things going on. Okay. With that other one, this is what that looks like. It's really hard to go through and see. If I go through and look at the differences in the mean, the differences in the means are the same, right? Here, whoops. I've got a mean difference of 5, okay? Also got a mean difference of 5. It's just much harder to see that because I've got so much spread in these scores, okay? And so when we start thinking about our group-based data, thinking about any variability that we see within a group is error. Because if the only thing that's determining scores is Jayla's manipulation, then everybody should be about at the same level. And if I'm not right at the mean, what is that? That's unexplained error that I can't account for in my model, right? It's just fuzz. And so what we want to do with means-based analysis is groups with lower variability are nice because they separate much easier. You start to see things a little bit better, okay? Now, with enough people in my sample, this will sort of identify as population differences, but the effect size is going to be pretty small versus that, where it's going to have a pretty strong effect size with things. Don't worry about that. We haven't got into that. We'll sort of worry about that when we get to that piece of things. And questions about this? All right. So characteristics of standard deviation. Okay. If I add or subtract a constant from each score in the distribution, it doesn't change the standard deviation. Okay. I've got a set of scores 1 to 10. I've got a standard deviation of 2. If I go through and I add a score of 5 to all of those, my standard deviation is still 2, right? Everything just kind of shifts up the scale. There's no happening, okay? But if I multiply or divide each score by a constant, that's going to cause the standard deviation to change by that constant, right? So I've got scores with a mean of 5 and a standard deviation of 2, and I multiply everything by 10. Cindy, what's my new mean? If it was 5 and I multiply all the scores by 10, what's the new mean of my distribution? What's that? Yeah, so I've got a mean of 5 and a standard deviation of 2 in my original scores. I multiply all scores by 10. My mean was 5. What is it now when I multiply everything by 10? 50, yep, right. And my standard deviation was 2. What's my new standard deviation once I multiply everything by 10? 20, yeah, right. It goes through and sort of multiplies everything. Now, if I go through and I have a sort of mean of 5, a standard deviation of 2, Jack, and I add 10 to every score, what's my new mean?
The mean is whatever it was plus 10, but it's not a
So it's
deviation.
15, right? And what about the standard deviation?
It doesn't
It
change.
change, right? It's still 2, right? So again, just thinking about in terms of transforms and moving back and forth and navigating results, so understanding scaling what things are doing starts to become really, really useful for Not everything that people will report in publications is what you need or want. What you want to be able to do is reverse engineer stuff to be able to bend it to your will and sort of use it for your purposes. This starts to become a very, very useful skill. And sort of knowing how things are calculated starts to become really, really useful with this. All right. Some factors that influence variability. Okay. Extreme scores. Okay. Range, variance, standard deviation, all this is influenced by extreme scores. If I get scores hanging way out at the margins, it's going to go through and it's going to impact all of it. Sample size. Range increases with sample size, right? As my sample gets bigger and bigger and bigger, my range is going to get bigger and bigger and bigger, but my variance and my standard deviation remain relatively unaffected. Why is this? William, why would my range get bigger and bigger and bigger as my sample size increases?
You're just more likely, if you kind of go back to the norm curve we were just talking about, you're more likely to have people kind of on the outskirts of that, or who are, you know, in that 2.5 to 3 standard deviations away. But if they were in those kind of general distributions in those 2.5 to 3 standard deviations away, it could still keep your standard deviation the same.
Yeah. So I'm going to go through as that sample gets bigger and bigger and bigger. I'm more likely to capture the folks on the end, which is going to make my range get bigger. But my standard deviation, my variance should stay pretty stable, right? Because the calculation of standard deviation and variance should account for sort of the fact of that sample size, right? Because you're dividing it by n, you're sort of getting that. And if it's a good population estimate, they should be sort of pretty stable across sort of different sample sizes, right? Range can fluctuate unpredictably across samples. Again, standard deviation and variance are pretty stable, right? From sample to sample to sample to sample, who knows if I'm going to capture someone who's really, really small or really, really big. Again, as soon as I get one person, that's going to shift that range jump around all over the place. Again, standard deviation and variance are going to stay pretty stable across samples. Now, in terms of open-ended distributions with those censored data, right, 100 plus, I actually can't calculate any of that, right? So again, one of those things you need to be careful with when you're building experiments, because you'll see it a lot in surveys. It'll be like you have a continuous where there's a couple things going on. One, I've got a continuous variable that I'm chunking into bins, which may be nice for sort of fitting something on a survey. In terms of actual data analysis, starts to make it really hard, right? Because there's a bunch of, I just added fuzz in there that I don't know what to do with. And then from an analytics standpoint, there are ways to deal with that type of data, but it starts to get complicated. And so as you're going through and developing experience, always be careful with censored stuff. Ask yourself, how do I want to use this? And is that amenable for sort of the types of analysis I want to want? So it's kind of a dangerous thing. So like at your own risk, if it's purely descriptive, you're not going to use it for the analysis type of stuff. Awesome, whatever, right? But if you want to incorporate that as a variable in anything, that starts to get really tricky. So just watch out for it, because you can't actually calculate an actual variance estimate on that, because it's not going to get anything that's super meaningful. All right. So we got means and variance. Okay, how are we feeling with this? Okay, it's kind of like drinking out of a fire hose. Here's an entire like half a semester of undergrad statistics lecture. Right, that's all right. So we're talking about central tendency, variability, but when we're looking at distributions, we also want to be able to describe shape. Okay, if we're talking about, and there are different terms we use to talk about shapes of distributions. Okay. Symmetry is one property that we use to go through and describe distributions. Here we've got a normal curve. This is a wonderful, beautiful, symmetrical distribution. And we fold it in half. It's the same on either side. If I know what's happening on one side of things, I know what's happening on the other side of things. Here we've got a nice symmetrical distribution with the mean, median, and mode all lined up on the same line. Here we also have symmetrical but non-normal distributions. These don't occur so often in real life, but you can, right? Here we've got got a bimodal distribution, a multimodal distribution. My mean and median is identical with both of these. My modes are different places here, but still symmetrical in that I could sort of fold this in half and I get the same thing on either side of the center line. Here is another symmetrical distribution, but one that's not normal. Catherine, what's going on with this distribution? Yeah, right. We've talked about this as a square distribution, right? And this is your distribution is going to have high negative kurtosis. We'll get to that, right? But it's basically I've systematically gathered four observations at each one of these values, right? We've got fixed effect sampling right here, right? But everybody is exactly the same across these. My mean and my median are all sort of the same place. It's perfectly symmetrical, but it's a different type of a shape than sort of my multimodal arrow. So again, that's a good thing to have in your vocabulary is square distribution, right? Flat across the boxing. But we can also have non-symmetrical distributions, okay? And one of the ways we will describe this is using indices of skew, okay? Skew, this is my third population moment. This is more like sort of our trivia stuff, know what it means. And if you run into methods papers that are talking about population moments, this is what it's about, right? More so than should I need you to like be experts in this is just to give you vocabulary for things that you may run into in terms of different methods papers. But skew determines or is described as the symmetry of our distribution. As talked about before, think about distribution. Sometimes people get this turned around. Skew is determined by the direction of the tail. Okay, tail stretches towards higher values. We got positive skew. Tail stretches toward negative values. We've got a negative skew. Okay, examples here. The thing to remember is if we've got a distribution that has high levels of skew, and high is a relative term and just really kind of is based on your assessment of the situation. But the mean is no longer a valid index of central tendency if I've got a mean with some sort of noticeable serious skew. Okay, again, we talked about this. Mean will be stretched out farthest towards the tail. Mode will be far right or left, depending on where the skew, which direction the skew is, and your median is going to fall somewhere in between the mean and the mode. So again, for skew distributions, classically we're going to go through and perhaps select a measure of central tendency, or select median as a measure of central tendency. Now, depending on this, is all context dependent. Again, this isn't just like, well, I won't go through and I see that my skew is not exactly zero, therefore I automatically have to switch over to medians. No, don't do that. Don't make things overly complicated, right? If I have a distribution that's okay, but it's kind of got a slight skew one way or the other, mean is still probably fine. If I'm measuring something like housing price or income or like sort of stuff that people measure in economics or things like that, sort of alcohol use stuff, reaction time. Now all of a sudden, median is probably a better bet because things are sort of very, very noticeably skewed out in our direction. You just want to think carefully about that. People comfortable with skew? Kind of this is as an idea. Okay. Other thing we want to go through and talk about kurtosis. Okay, kurtosis is your fourth population moment. Describes the shoulder of the peaks of the distribution. Okay. Positive kurtosis. This is going to be a distribution, heavy tails and a narrow peak. This is kind of what we are seeing right here, as opposed to a nice normal rounded bell curve. We got something that's kind of pointy with little skinny shoulders, and then just kind of some like wing tails that come out here. We got thick tails and a skinny shoulder and a narrow peak. Okay, different than negative kurtosis, or sort of the statistical term is platykurtic, leptokurtic and platykurtic. Negative kurtosis, platykurtic. Here we got a distribution with a flattened center, heavy shoulder, kind of dome shaped. Okay, I don't actually have tails. Everything just kind of sort of shuts down, right? I've got kind of this sort of kind of boulder looking distribution going on with my negative kurtosis. So again, describe, the peak in the shoulders of your distribution relative to normal curve. Here's the thing. Kurtosis, if you've got kurtosis that in your sample that is not seen in the population, the concern is that kurtosis tends to underestimate population variance, okay? It's pretty obvious in the negative kurtosis, right? Why we might underestimate population variance because we're not sort of getting the tails, right? But our positive kurtosis also underestimates population variance. Why is, I mean, we've got these thick, heavy tails sort of stretching out. Where are we underestimating variability in my positive kurtosis and my leptokurtic distribution? Charlotte?
There's around the, I don't know if the mean or wherever the
Yeah, right.
average is, yeah.
We're missing this part, right? Like you think about like, oh, look at these thick tails that are coming out, like, yeah, but there's only so many values out there, right? What we're missing here is all this variability that should be going on here, that's not, that it's all contained. And so it doesn't matter if we're talking about positive kurtosis or negative kurtosis, the concern is that if this is not reflective of the actual shape of the distribution, what we're doing is we're underestimating variance with this. Okay. So again, this can impact the quality of variance tests, it can go through and impact parameter estimates, screw with your standard errors, we'll get to what that is in a few sessions, but some sort of things to be thinking about in terms of kurtotic distributions. Question about kurtosis. This is, you got a kurtotic distribution here, like your square distribution, right? Like it's not kind of got a dome shape, but it's just flat. There is no peak. It's sort of really square shoulders. This is kind of what's going on with this piece of things. So as we go through and we'll go through and we will get indices of skew and kurtosis based on our statistical software. And has anybody gone through and done this with or read papers where people are going through and reporting tests of skew and kurtosis? Yeah, ish. People reporting p-values, talking about significant kurtosis, things along those lines. Yeah, Kate, where did you see that?
I'm sure there was a paper that I read at one point, but I know with the one data set that my advisor sent me over the summer that I was working with, I was just testing for normality. And so that comes up as like a test. And so you're looking at p-values for that. And I think if it's like a p-value less than 0.05, then it's kurtotic. You're not normal. It's a not normal distribution.
I will never ask you and encourage you never to do that with your data set. Okay? The issue is what we would do is we can get indices of skew and kurtosis of your data. Okay. The assumption of your test is not that your data are perfectly distributed, right? The assumption is that any data you collect has a skew of 0 and a kurtosis of 0. And if I get a big enough sample, if I start to see minor deviations off of normality, it'll still flag those as significant. And someone will see significant as being interesting and important. And then they switch over and do a bunch of weird non-parametric stuff that you don't screw around with, right? What's more important with looking at skew and kurtosis is one, look at your data, like actually look at the visual representation of the data and see what's going on. And then two, go through and think about, look, what's the absolute value, what's the absolute deviation from normality, and then think what are the assumptions of my tests that I want to go through. Right? So again, as a general rule of thumb, these are not bright line. I will not give you bright line. If you get like a fraction of an inch over this, it's problematic. And if you get a fraction of an inch under it, then it's not problematic. This all exists on a continuum, and it's a judgment call on a lot of, like, your standard for being able to make an argument for whether or not something is problematic or not is to be able to stand up in front of colleagues that you respect to make an argument for this is a problem, right? If you can't do that with a straight face, or you're not sure how to do it, so then you need to go through and sort of refine sort of arguments for screening things. Okay. What we want to do is go through and say about skew and kurtosis of about 2-ish are kind of like general guidelines for what is. I will use this to write this down, problematic deviations from normality, right? What you see, and I've done this before. I've been like, oh, so skew and kurtosis is less than 2, so a relatively normal distribution. You will see if you get a skew value of anything even close to 2, it's very much not normal at all, right? So saying it approximates normality is not true. What we're talking about is this deviating from normality to the point where I'm starting to become thinking that I need to be working on something. Okay. What happens if, again, situations where someone says, oh, I went through and did a test of normality, and the test of normality came up as significant equals p less than 0.05. And so then I went through and did a whole bunch of screwy stuff or transforms or things along those lines. That starts to get problematic, and then you probably made things a lot more complicated than you had to when the deviation from normality, particularly if you have a large sample, was probably trivial and not something that warranted you needing to go through and do that stuff, right? So what we're wanting to be focused more on is the absolute value of this. Okay. So thinking as you're going through, and this will start to become as you're working through and getting language with stuff, thinking about like, hey, we're looking at this. And we clearly have some problems in terms of, or so that it's clearly not normal. But is that not normal a problem for the analyses that I intend to go through and run? And then making decisions from there. Okay. Now, if you go through and say skew less than 2 and kurtosis less than 8, if I got sufficiently large samples, I can interpret this as non-problematic. But I've done this before, just because and it probably didn't make a difference. And I went through and ran it like it didn't make a difference, but like standing in front of your colleagues with a straight face and making this argument, I don't know if I would do that in front. But I guess I publish a paper like that. But like it's just like this is getting it. But it's playing with bright line sort of things that people put down. And like, so if I can attach something to a reference, a lot of people will say like, oh, I guess it's fine. What I want you to be doing is thinking carefully about what this means, what the implications are. So, okay. Questions about this? Okay, did not set you up to be like, hey, who did this wrong? I'm just thinking, no, it's a common practice and something that sort of people will inadvertently do in an effort to be rigorous in their analyses, but end up making something. I went through and did a bunch of transforms that I didn't need to do, and now interpretation is more complicated than I need to. Or I went through and I had to figure out a bunch of like weird esoteric non-parametric statistics. A lot of times when I'm reviewing papers, I'm like, I just report what the skew and kurtosis was. Well, skew was like 1.2 and kurtosis was 1.8. Like awesome, just run your t-test. Like you don't have to worry about that. T-tests don't actually make any assumptions about the distribution of your observed data, so don't make things more complicated than you need to.
Yeah, I was doing it like because I was doing a lot of self-teaching on YouTube, and so they're like did the tests, and then I presented to Jared, and Jared's like, yeah, just ignore that, or not ignore it, but it's like they're really sensitive. So
right, again. A statistical test almost always is just going to tell you whether or not something is equal to 0. And no one ever said that your assumption of your test had to be that your skew is exactly 0 and your kurtosis is exactly 0. Particularly if you've got really large samples, your skew and kurtosis will almost certainly be something that's not exactly 0. That has no bearing on anything, right? So just want to think carefully about what we're doing, why we're checking it, what the mean is, and things along those lines. All right. Other thing that happens to working this stuff, for statistics, large samples are a fix for a lot of stuff. If you've got enough people in your sample, a lot of this stuff starts to go away in terms of having to be concerned about things. So again, this is from the PSYC and the Dell. So large samples, positive kurtosis, you got a sample of over 100, starts to become something I'm not super worried about. Negative kurtosis, couple hundred, super worried about this, right? So this is more for regression-based analyses than sort of means-based types of things. So we'll go through, we'll assess skew, kurtosis, we'll note it, so we'll describe it, we'll talk about it, we'll make it determine whether or not it's sort of something that's important or not. But for our means-based analyses, that will be. Okay. So again, one thing I can do not in this class, like we'll go through and talk about guidelines, talk about interpretive benchmarks. do not assume that anything is a bright line. It's like, because you've got a Z value that exceeds 3.29 does not mean 3.3 doesn't mean like, oh, this is a terrible outlier that we have to throw out, versus if it's 3.28 that you are fine with it, right? These are gradients. You have to look at your data, think about things in context to determine whether or not is this a problem or is it not. This is Tara sort of looking at you for right justifications. She doesn't like that picture. She's like, I was very happy that day. I was like, you were. All right. Extreme values. Okay. I prefer not to use outlier as a term. Although sometimes, so I have it here, it's a univariate outlier. So the problem with that is calling something as an outlier, it sort of gives it a status. This seems like, oh, this is a thing versus not a thing. And like anything else, this is just, it's on a continuum, right? And a lot of it depends on context, right? Extreme value seems less definitive. It's just like, oh, hey, this is a large score, or a very small score, right? Yeah, I feel like it gives us a little bit more flexibility in terms of how we're thinking about things. Words matter, right? If we're talking about a univariate outlier, I'm talking about an extreme value on here. I've got a distribution, here it is. I've got an extreme value, or I've got a univariate outlier that just means it's an extreme value on that particular whatever measure it is we're looking at. Okay. Causes of extreme values. First thing you're going to do is you're going to detect it in your distributions. You can say visually back, oh, I got a really large score. Next step, most important step, is identifying what's going on with this. Okay, and this starts to become critical. One could be incorrect data entry. Things are done online, and so we have less than when I was in graduate school. We had an army of research assistants have like a questionnaire packet that and like students or undergrads going through and like typing into a spreadsheet like all of those things, right? That's going to result in errors, right? And sometimes you can get sort of problems with things, right? So always have access to your hard copies to be able to go through and check, like, was this just a misstep in terms of entry? This is a big one, and this will often be what's happening. Okay. Or it'll be a score where, and this will happen if you haven't seen it yet, you have a questionnaire and you have sort of 0, 1, 2, 3, 4, 5, and someone like writing 6 and circle it big. It's just, you don't get to make up your own categories with stuff. So, but sort of a unaware research assistant may enter like, well, they said 6, so 6 is what goes in. 5 is the top that they can have, right? So always go through and be able to go through and double check stuff. Other thing that can happen, I do this all the time in SPSS, not in Stata, in SPSS, you can go through and enter data codes that the system will read as missing data. And when I'm going through and entering data, if I see a data set and there's just a missing value, I don't know what that means. Is it that the person didn't respond to that? Or did someone forget to enter it? Did it get accidentally deleted? Just a sort of a missing value. It could be a number of different things. So what I do is I'll have a code for missing values 999. 999 just means someone didn't answer that. 999 is rarely a real value for anything. And so if that's just punched in the data set, I can go through and take a look and say, all right, we got people who, I know that this means that someone didn't respond to this item, or it decreases ambiguity. But if I don't tell SPSS to treat 999 codes as missing data, what it'll do is it'll treat it as a score of 999 and you get wild stuff, right? So go through and make sure that that's sort of not something that's happened. Sometimes, we've talked about this, cases in a member of the intended population of study, right? I went through, collect my sample. I've got a wild score, but if I go through and look through the file, like, oh, this person is not someone who I'm interested in, right? So I go through and I'm looking at, say, undergraduate income and looking at stress and mental health and sort of things along those lines, right? And I see most of the, so like maybe reported income that you would expect from 18, 19, 20-year-olds who are in college. and then someone who's sort of like reporting six figures. Okay, so what's that, right? You go through and it's someone like a sort of a retired person who's taking auditing class or something like that, right? Cool. I get rid of that person because that's not someone I'm interested in. They're not representative of my population of interest. We'll get rid of that person. Okay. That's an easy fix, but you got to be able to sort of make sure that you can go back through and sort of take a look and see like what's happening with this. Okay. Last thing, case can be a member of the intended population, but it's something that's underestimated in the sample. Okay. Let's say, Jill, you're looking at misdemeanors among undergraduates and thinking about how interactions with law enforcement impact education or things along those lines. So you got a sample of people, ask if they've ever been sort of had tickets or sort of things along those lines. You've got like a scale or something like that. And so most people sort of have drinking offenses, status offenses, like things along those lines, right? And then you've got someone who had something pretty heavy, maybe prison or something along those lines, right? Maybe you are actually interested in those people because that's actually kind of an important thing to your study. It's just there's not that many of those folks out there, and you happen to capture a couple of folks. So they are the population of interest. We just don't have, we have a limited sample. We don't have some people kind of filling in that gap, right? This is a more tricky thing. How do I go through and navigate that, right? I don't want to just scrap them because they're actually people I'm really interested in. If I just let them hang out way on the margins, they're going to screw everything up, right? So then we have to get creative and thinking about smoothing procedures, maybe some transforms, although so that starts to get tricky. But then that starts to become a more difficult sort of situation. How do I go through and address this? So, but if we don't go through and we just sort of forge ahead and pretend that those things aren't there, or don't look for them, what we can do is have those individual observations having undue influence on any of my coefficients that I'm estimating, right? If I have any sort of a result from an analysis that is completely dependent on one or two observations, that's bad news. That's not a stable result. And that's like, I should not be able to like pull out or put someone in and have it dramatically changing my results. If I can, that's not a stable solution. It's something that's causing problems. Okay. I can have problems with both my type 1 and type 2 errors. We'll talk about that. And what I get is reduced generalizability of my solution. Right. So that might be Jayla, in your case, someone you want to keep in, you're like, well, I'm just going to run with it. What you might get is a model that fits your data and no other data that will ever be collected in the universe, right? And so now that starts to become a problem in terms of interpretation and generalization, and sort of whether or not I've documented something that's capturing a generalizable concept or phenomenon versus something that's a parlor trick that sort of works out in this data set, but nothing else in the universe, right? So wanting to think carefully about that. Now, the nice thing is, because of the stuff that we tend to study in behavioral sciences, it's hard to get like really problematic stuff. There are certain areas where we can. Most of the time we'll get extreme values, and most of the time if we work with undergrad, you want to be like, is this someone who is serious or was someone not paying attention, right? So you want to have more data to be able to go through. If I look through and this person is way out there and they just like kind of seed everything out and make, okay, well, that person's not a reliable report, I pitch them out, right? Or someone who the rest of their scores don't make any sense with. So I think this is someone who either wasn't paying attention or screwing around or just didn't understand the task. And so maybe, but anytime you go through and start making adjustments with scores, either throwing things out or smoothing or doing anything like that, you want to be very clear that you can tell people, here's what went on, here's what we did with it. And then we can have a sort of professional discussion on whether or not that was a good approach or not a good approach, but be able to document, not just be like, hey, this person did something I didn't like, so I threw them out. This person acted inconsistent with my hypotheses and it was messing with my analysis, so I just got rid of them. That's not a reasonable response to things. So just making sure you keep good records so that you know and can be able to go through and track stuff down. Yeah, Finn.
How do you kind of like determine the ethics and logic between like, is this reliable and is it not? Because I feel like that's confusing.
Like what can I defend? right? If I can sort of say to a journal audience, here are the people I threw out because of X, Y, and Z. And if it's a couple people, it's probably not a big deal. If it's half your sample, then that's probably a harder thing to defend, right? And again, the presence or absence of a handful of folks should not make a difference. And if I go through and I take a look and p-values are all small on whatever they're doing, it's fine. If it's like, oh, hey, I got rid of these 3 jokers and now my stuff kicks over into p.049, then I start to maybe worry if you're playing with data a little bit. But hopefully the types of things that are most important to your study are going to be consistent whether or not you have those people in or out, or if having them in like really makes things not make sense, you can go through and say, no, I went through and took a look at this person, report high levels of this and low levels of this, which is inconsistent with anything in the universe, so they're not reliable. Or Cindy, we're doing maybe an assessment, so this person was like involved in some legal stuff that they said, and then they just denied everything across the board despite reporting this and another thing. I don't know what's going on, but yeah, we just lost that person, right? Those are the types of arguments you can make. So yeah, professional judgment is largely what that comes down to. Yeah.
Well, I was gonna say, like, eligibility criteria give you a really good backbone for removing people too. Like if people lie on an eligibility screener, that gives you like pretty strong grounds to stand on ethically and for a journal board of like why you remove them.
And I've never had problems with sort of journal people saying like, oh, hey, because one, I'm not throwing out a lot. I see, because I just don't want to go through the essay and try to describe it in a paper like why I threw some people out, because to do it responsibly, you have to, a reasonable person should be able to go through and read and understand your reasons. And if I go through and I have like outliers and things like that and I run up with them without them, it doesn't really change anything. But so long as they're not, if they're flagrantly bad responses, then I mean, you can throw that out, right? But if they're sort of like maybe more extreme values and they just like, yeah, they came out as weird observations, but it didn't impact anything, so we just left them in there, right? To be more inclusive as opposed to less. So, yeah. Other questions? All right, cool. Other thing to keep in mind, we don't think about this a lot, but we can have extreme values with categorical data, okay? If I have dichotomous variables that have wild splits, like we're talking like 9-to-1, what we've got is it's a dichotomous variable. It's just a 0-1 code, but what we've got is a situation where we've got categorical data that is technically an outlier, right? What happens is within these data, the cases in the smaller category have much more influence on any individual in the smaller category has much more influence on the outcome than any one individual in the larger category. Talk about this as the Wyoming Senate effect, right? We've got 500,000 people in the state, but we still have the same representation in the Senate as California and New York. Like any single person in Wyoming has, by definition, greater power in the Senate than any individual person in California or New York or sort of big state or Texas or any place like that, right? So thinking about the same thing in our data, right? We want to be careful with that. Now we can tolerate pretty extreme splits, like it doesn't have to be exactly 50-50. But if we're getting like 9-to-1, it starts to become problematic. Okay. What this can do is it can attenuate or sort of reduce associations with other variables. It can create sort of spurious associations. And unless it's something that's critical to your analyses, you should probably get rid of it, right? And not it. Where this comes up most often in our research is when we want to look at sort of characteristics of different groups, particularly if we've collected homogeneous samples, right? We do things like, oh, here's our white non-Hispanic folks, and then here's everybody else, right? One, this is not an interpretive group or an interpretable group. I don't know what this group means. Also, we've got a wild split. That's right. If you wanted to look at that, you needed to come up with a plan on the front end to be able to go through and get reasonable representation over sampling certain groups to make sure that you've got that in, so you can meaningfully incorporate that into your analysis, right? Doing this as an afterthought on the back end is gonna get you into trouble, because even if you do go through and identify a difference there, I don't know what to make of that, right? Because it's white non-Hispanic folks versus everybody else. I gotta have a really good reason why that's a comparison that makes some sense and is interesting and meaningful, right? Same thing here, sort of men and women. Here we've got yeah, sort of 9-to-1 split here. Like if I want to look at sex differences in that, nope, I don't have enough representation there. These 31 dudes are having way more of an impact on anything than sample. Again, if I was interested in sex differences, I need to make sure I got a more balanced sample. I need to sort of take some steps to go over and to make sure I'm capturing this, to throw this in on the back end of not gonna be an okay thing to do, right? I just don't know what it's gonna be, and it's probably not gonna be anything that's generalizable or useful, okay? So just wanna be really, really careful with this. So in addition, when you're screening, we wanna look for extreme values and extreme scores in our continuous variables, but also remember that we can run into problems with categorical data as well. So again, if I'm thinking about extreme values with my continuous data, what we're gonna do is we're gonna go through and we're gonna calculate Z-scores. Z-scores should be a way to go through and describe how far out this score is, okay? We're gonna use sort of some general benchmarks for identifying things as starting to become increasingly large. But again, no bright line sort of criteria. It's gonna be you looking at your data, think about what you're measuring, thinking about how you're measured it, thinking about what the rest of the distribution looks like. If I've got things that kind of trail off in a histogram and then they kind of taper off and then got some stuff there, yeah, these scores at the end might be extreme scores, but they're just kind of part of a continuous distribution. I'm less concerned about that than something that goes through, here's my distribution, big gap, and then I got some folks hanging out here on the ends with like islands hanging out here. That's more of a concern than something that starts to be a continuous distribution, because I got a big chunk of scores that aren't defined by anybody. It's just a massive void, and then some folks popping up at the end. That starts to become more concerning to me. Something that kind of trails off into a tail. Okay. So again, we're going to look at our graphical representations, and then we're going to go through and we're going to look at standardized scores to go through and say, I've found a number of scores that are above sort of this point, right? But again, we're not going to use bright line interpretation to go, oh, this is an outlier because it's above a certain score. We also need to recognize that if I get a large sample, by definition, I'm going to get some observations that are out there, right? And if that happens, that just means you have a large sample and you probably got a good sample if there are some scores out there. But if I have a really, really large sample, am I super concerned about any individual score? Nope. Again, not in the data that we collect. Again, if I'm looking at income and I've got sort of Zuckerberg and Gates and sort of those folks hanging like orders of magnitude out from anywhere, yeah, right. But that's not the types of things we tend to sort of go through and look at. So for our large samples, almost always account for some concern that we see there. Yeah. So different ways to go through and to display data. Bar graphs, just straightforward, useful for presenting distributions and categorical data, differences in experimental conditions, things along those lines. Here's we've got sort of presented breakdown of our groups, right? So that's useful if you wanted to just do that. Here we've got an experimental data set. We've got different conditions, right? We've gone through, got confidence intervals around this. So bar graphs are nice. Histograms. Histograms are most usefully used to demonstrate distributions. This is nice, right? So here's some PTSD data where we've got mean, median, mode, skewed, standard deviation, skewed kurtosis, kind of seeing everything going on right here. Is this a normal distribution? No, but we've got a little bit of negative skew, some negative kurtosis, it's a little bit boxy. But are we worried about this distribution? No, that's fine. This one, maybe a little bit more, right? Here we've got mean, median, mode, standard deviation, these are z-scores. Skew 2.4, kurtosis 6.8, so like really leptokurtic positive kurtosis with this like tall peak and kind of flat tails. Here we've got some positive skew heading out here. Depending on what type of analysis we're doing, this might be more of a concern. This is completely fine. These are just histograms. Nice way to go through and just present distributions of our continuous scores. Problem with histograms is depending on how you go through and bin these graphs, it can wildly change what your distribution looks like. Okay. SPSS has some decent defaults. Stata defaults are not so great, but we've got some guidelines for that. But you can have the same data, very different histograms depending on how you bin that data. What then becomes nice then is looking at box plots. Okay, box plots, no matter what program you're doing, because box plots are created with a standard set of rules. Okay. You've got here a couple of box plots. We've got some pre-post data on some stuff. The midline here in your box plot, this is indicating your median. Okay, write this down. Box plots are median-based plots. It's not your mean, it's not your variance, your standard deviation. These are median-based statistics with your box plots. Center line is your median. The bounds are your box. So this, so top and this bottom, these are your first and your third quartiles. Okay. So the distance between your box here, this is your interquartile range. That's your middle 50. This is where your 50% of your values are falling between the first and your third quartile. Your whiskers, this is where things start getting complicated. Your whiskers, also known as your inner fence, can be a couple of different things. They're either going to represent the minimum or maximum values of your data set, or they can tell you where your values, your most extreme values that remain within plus or minus 1.5 times your quartile range. And so in this situation, my whiskers here, my inner fence, whiskers are indicating so the min and the max values here. Okay. Extreme values, if there were extreme values, these are going to be cases that extend beyond my whiskers. These points that extend beyond my whiskers. You're going to see these as dots. In SPSS, you get asterisks that are more than 3 times the interquartile range beyond here. Here, we don't see any dots. So this is just the whiskers are your min and max value for these two groups. And what we would see is we would expect with a reasonably normal distribution, about 95% of your data should fall within the whiskers. So we're looking at this, right? Pretty straightforward. Median, first and third quartiles, right? Here we got min, max. But here for this last condition, we've got a couple of scores hanging out here, right? Things change. This is not the min and the max value. This is the farthest score, the most extreme score that still falls within 1.5 times the interquartile range. Here's the lowest score that still falls within 1.5 times the interquartile range. And then these two dots are cases that fall beyond that. Okay. So here, if I'm going through and taking a look, even Steven across these groups, slightly larger sort of range in some of these and others, but these are all looking fairly comparable, right? Like this one here, we've got a couple more extreme scores, but I don't know if that's anything meaningful. That's just kind of maybe a characteristic of the sample.
If like the value 184 and 123, if there's one, there's always gonna be another one at that.
I don't know. We could just have this one, and then if the whisker hit the minimums value, that minimum value is still within 1.5 times the interquartile range, and then this is just something that's popped above. Yeah, Finn.
I'm sorry if I'm missing something, but how do you figure out when the min and the max will fall, like within the whiskers versus when they're gonna be beyond?
Oh, yeah. Here, there's no other dots. That way, it's just the min and the max by definition. If there were anything beyond that, they would pop up on the graph.
Okay.
Here, min, max. But here we're seeing dots. That means we've got something beyond 1.5 times the range.
Thank you.
Then we get something like this, right? Now, all of a sudden, we got something different going, right? Here, we've got median values down here. Minimum is 0 across the board. And now we've got a lot of, sort of points up here. Anything within 1.5 times the interquartile range are dots. Things that are beyond that are asterisks. These are things that are beyond 3 times the interquartile range. So what kind of data, what type of scores are we getting here in terms of distributions? What's the shape of those distributions?
I would say like abnormal distribution.
Okay, so not normal, yeah, because they're not symmetrical. Specifically, what types of distributions are we seeing? Okay. Positively skewed, yeah. Down here is the bulk of where everything's at, and things are sort of stretching out towards the top, right? So we're seeing positive skew with these data here. Questions about the box plot? Right. Know the box plot, love the box plot. You'll do a lot of stuff with the box plot in terms of screening. It's just a nice way to go through and report graphically what's going on in ways that are going to be consistent, not dependent on how your program has been your stuff. Jalen.
Sorry, so the asterisks, those are the more extreme.
Yeah,
the
these are
value.
values that are falling beyond three times the interquartile range. So this distance here, this is falling more than 3 of these above. All right. So just some final thoughts, quotes, things like that in terms of how we're thinking about our analyses, how we're going to go through and work on stuff, thinking about, people like, oh, statistics are boring, and it's just sort of like, it's cut and dry. I'm a creative, right brain person. This is still, if you're sort of approaching this as machine style, looking for a decision tree, what do I make the right answer in the right direction? You're gonna be screwed, right? It's gonna be like, okay, here's my set of options. How do I think about context, what I'm trying to do, what this means? And oftentimes with applied analysis, it's trying to choose the least bad option and the stuff that's available to you, right? Which isn't great, but if the alternative is like, let's not do research, then let's just do the thing that sort of gets us as far as we can while acknowledging the limitations of this approach. We did it this way. Here are the things we can be careful of, but this is kind of what we found. Okay. So, and again, thinking about the planning phases, you're also putting together theses, dissertations, things along those lines, being mindful and thinking about what do I want to do, then how do I want to analyze this, and what does that mean for how do I want to go through and measure these variables and pull things together, being careful with that and stuff. Okay. Bright line statistical guidelines are not the boss of us. We get to go through and make our own decisions on to whether or not we are close enough to the bright line or far away from the bright line. Taking lots of stuff into account, sort of trying to determine whether or not something's a problem or not. So again, just being in charge and being purposeful and intentional about our decisions and communicating that to our readers and our sort of people on our committees and things like that. And then we can have a discussion on whether or not you like what I did or not. But at least I did what I did for a reason. I probably already thought about the thing that you're going to suggest, and I didn't do it for a reason. And I communicate that, right? That's a better place to be when you're sort of in a committee meeting than just thinking about like, oh, I'm getting peppered with alternatives that I didn't consider because I didn't think carefully about the stuff. So, all right, awesome. That's it. We're finished up. We're on target. We covered much more today than yesterday, but so take home points at the end of this. Shall we go through, just take a look, so make sure that you're kind of on point, sort of covering it, or sort of like have a handle on this stuff. And if you do, be in a good spot. So